Picture this scene. You are standing in the northernmost reaches of Japan, on the island of Hokkaido. By all accounts, this place is the definition of pastoral tranquility.
Almost idyllic, right?
Exactly. In the summer, it's endless fields of lavender and sunflowers. In the winter, it's a silent, snow-covered haven for skiers. It's a region so devoted to the slow life that it produces half of the country's milk. And locals even have this somewhat resigned saying, people who come to Hokkaido eventually leave.
A kind of brain drain baked into the culture.
Right. But if you look just past those quiet dairy farms today, that peaceful narrative completely shatters. Instead of barns, the skyline is suddenly dominated by heavy industrial cranes.
A very different picture.
In the small city of Chitose, the ground is shaking, not from an earthquake, but from a construction frenzy. Billions of dollars are being poured into the earth to build something that seems completely out of place in this rural landscape. A futuristic fortress designed to mass-produce 2-nanometer computer chips.
A technology so advanced that even a titan like Intel hasn't fully mastered it yet.
The contrast is just jarring. You have this company called Rapidus, led by a man who insists this high-tech megafactory will be covered in grass to blend in with nature, yet the ambition behind it is aggressive and loud. They are trying to resurrect Japan's lost era of tech dominance from the 1980s in a single high-stakes leap.
It really leaves you staring at this construction site and just wondering.
Is this the birth of a new Silicon Valley of the North? Or is Japan burying billions of dollars into a snowy field in a desperate attempt to turn back the clock?
And that really is the central question.
That is the core question driving this deep dive. We're looking at a $32 billion gamble collision between tranquil dairyland and a high-stakes 2-nanometer chip fortress. This isn't just about constructing a factory.
No, it's much bigger than that.
It is Japan's last chance effort to reclaim technological leadership, a status they decisively lost after the 1980s. Our mission today is to unpack this historic moment, analyzing the sheer economic necessity, the geopolitical pressures driving the urgent timing, the colossal technical challenges of the 2-nanometer leap, and the profound social and economic transformation intended for Hokkaido itself.
We really need to understand not just what they're building, but why they are building it with such urgency.
And what happens if this immense high-risk effort fails?
It is an absolutely extraordinary pivot. And to truly grasp the monumental ambition and the urgency behind Rapidus, you have to appreciate the scale of Japan's historical decline in this sector. I mean, think back to the late 1980s.
Right.
Japan was fundamentally a global semiconductor powerhouse. Japanese firms, NEC, Toshiba, Hitachi, they were household names responsible for leading-edge innovation and accounting for over 50% of the world's chip manufacturing capacity.
50%. That's a staggering figure, particularly when you compare it to the present day where, global chip manufacturing dominance feels so concentrated in just a few places in East Asia. That level of control suggests not just market share, but real technological supremacy at the time.
It was complete supremacy, but that dominance began to rapidly erode. Fast forward to 2022, and Japan's share had plummeted to just 9%.
9.
Or maybe slightly above 10%, depending on how you measure it. But the point is, the decline wasn't gradual. It was a steep, steep drop driven by a complex interplay of economic, strategic, and geopolitical forces that started in the 1980s.
Okay, so let's start with that external pressure. The U.S.-Japan trade friction of the 1980s is often cited as a turning point. How exactly did that impact Japan's chip industry?
It was strategic warfare by agreement. Japan was absolutely dominating the market for dynamic random access memory, or DRAM chips.
The crucial ones, right? The high-volume commodity chips needed for computers and servers.
The very same. And U.S. manufacturers felt, well, existentially threatened by Japan's competitive pricing and their market penetration. The subsequent trade agreements, starting around 1986, were designed specifically to curb Japanese market share and protect American producers.
So that forced Japanese firms to pull back.
It forced them to reevaluate and ultimately reduce their massive investments in DRAM manufacturing, which, had been the engine of their technological advancement.
So geopolitical pressure squeezed them from the outside, but then domestic factors kind of sealed their fate when it came to staying ahead technologically, correct?
Absolutely. The geopolitical push was compounded by domestic stagnation. When Japan's post-bubble economy burst in the early 1990s, the financial caution that followed meant systemic underinvestment in the very area where rapid generational investment was needed.
Advanced fabrication capabilities.
Precisely. So while competitors like South Korea and Taiwan were building new fabs and aggressively pursuing smaller and smaller nodes, Japanese companies were just stuck.
And I remember their operational model played a role too. They held on to that old vertically integrated structure.
Yes. They were structured to design their own chips and manufacture their own chips, a vertical management structure. This proved incredibly inefficient compared to the specialized foundry model perfected by TSMC in Taiwan,
where they just focused on manufacturing for anyone who brought them a design.
Exactly. Japanese firms just couldn't keep pace with the nimble, high-volume specialization of the pure-play foundry. The result today is devastating. Japan's current domestic manufacturing capability lags significantly, operating at the 40-nanometer design rule.
40 nanometers, which, in terms of the cutting edge of manufacturing physics, that translates to roughly a 10-year technological gap behind global leaders like TSMC, which is already testing 2 millimeter.
Right.
So the Rapidus mission is not just about catching up. It's an unparalleled, high-risk leapfrog attempt to span a decade of lost ground in less than 5 years.
And that attempt is driven by pure necessity. The timing is absolutely critical because of the new geopolitical environment. I mean, the COVID-19 pandemic acted as this massive global shock.
Oh, for sure.
It exposed critical supply chain vulnerabilities that crippled the global automotive sector, electronics producers, and even healthcare device manufacturers. Semiconductors transitioned overnight from being a commodity item to being a strategic asset tied directly to national industrial resilience.
And this tension has only escalated with the rise of an increasingly assertive China and the ongoing US-China technology conflicts. Suddenly, controlling advanced chip production has become a core matter of strategic autonomy or economic security for every major economy.
That is the new mantra. The official framing is stark. We heard one NEDI official essentially summarizing the new reality by saying, the era where the world is at peace and it doesn't matter who supplies our semiconductors is over.
Wow.
So Japan has reacted decisively by enacting key policy shifts to mitigate strategic risk, most notably the Economic Security Promotion Act, or ESPA, passed in May 2022.
And this act provides the legal and financial backbone for these huge state-backed projects like Rapidus.
It does. It emphasizes the need to reduce reliance on potentially hostile or unstable supply sources.
What's truly fascinating about this shift is the recognition that Japan cannot possibly return to the isolationist, self-sufficient strategy of the past. The new policy just screams international collaboration.
It is the defining feature of this revival effort. The government recognizes that industrial self-sufficiency is, well, it's unattainable and possibly undesirable in the current global supply chain structure. Collaboration is now imperative, and it's financially incentivized through government subsidies.
And we see this in several key partnerships.
We do. First, the U.S. Joint Task Force, established in 2022, agreed on basic principles on semiconductor cooperation, focusing heavily on joint R&D and creating a more resilient, geographically diversified supply chain.
And Japan is also a foundational member of that informal U.S.-led alliance, the Fab Four.
Correct. The Fab Four includes the U.S., Japan, Taiwan, and South Korea, the four dominant players in the global semiconductor ecosystem outside of China. This alliance is all about coordinating policy and supply chain resilience. And the Japanese government is putting its money where its policy is.
Subsidies.
Huge subsidies. They're subsidizing up to 1/3 of the capital costs for designated manufacturing facilities.
And those subsidies are highly conditioned, aren't they?
Right.
They tie the financial support directly to the goals of economic security.
Absolutely. To receive this substantial government support, companies have to agree to two major conditions. First, they must commit to a minimum of 10 years of domestic production.
For long-term security.
Or long-term tech and job security, yes. Second, and this is crucial for strategic autonomy, they must prioritize domestic shipments during global shortages. This condition ensures that in a future supply crisis, Japan's own critical industries like automotive and electronics will be protected first.
So this isn't just a business investment.
No, it's a strategic national insurance policy paid for with billions of yen.
Okay, let's turn to the ground zero of this massive strategic effort, Hokkaido. We've established the necessity of the project, but why place a futuristic chip fortress in a snowy rural region like Chitose? It just seems counterintuitive when you think of the traditional hubs of high-tech manufacturing.
Well, the location choice was, in fact, highly rational. It was based entirely on the specific resource needs of advanced chip manufacturing. Semiconductor fabrication requires 5 core things: stable power, flat land, a trained workforce, access to a supply chain, and enormous quantities of ultra-pure water.
And water is perhaps the most immediate constraint, isn't it?
It is the absolute lifeblood of a fab. A single advanced semiconductor facility can consume millions of gallons of water per day. Hokkaido, with its vast natural reserves and established river systems, offers abundant, high-quality water resources that are, increasingly scarce in more developed regions of Japan.
The Rapidus CEO even pointed that out specifically.
He did. Koike Atsuyoshi explicitly highlighted it as a core advantage.
Beyond water, the climate itself plays a role, which is unique to a northern location.
Oh, a huge role. The naturally cool climate of Hokkaido is a massive operational benefit. Advanced semiconductor fabrication generates immense heat, right? And climate control and heat dissipation are major energy costs, often consuming a significant chunk of a fab's overall operating expense, especially in warmer climates like Taiwan or Arizona.
So building the facility in Chitose gives you natural year-round cooling.
Exactly. It significantly reduces the energy footprint and the cost.
And the final compelling advantage for Japan is geopolitical stability on a smaller, localized scale. I'm talking about seismic stability.
Exactly. Japan is notoriously seismically active. A major earthquake can destroy delicate billion-dollar machinery or, worse, halt production for months. The Chitose area, being in the northern part of Japan, has relatively lower seismic risk compared to potential sites further south.
So it offers greater operational security.
A key factor when you're trying to secure the global supply chain. This is why Koike emphasized the plan to blend the facility with nature, even planning for the factory to be covered in grass. It's an attempt to minimize the visual impact of this massive industrial intrusion, but the choice of location was driven by cold, hard operational logistics.
That attention to detail, down to covering the factory in grass, is clearly trying to harmonize a jarring clash. This peaceful countryside meeting the Industrial Revolution. But let's talk about the immediate seismic shift this is causing on the ground in Chitose. It sounds like a sudden, aggressive economic boom.
A shock to the system is a good way to put it.
Yeah, maybe even a shock.
It is an overwhelming financial shockwave. The Rapidus project alone is expected to see total investments reach approximately 5 trillion JPY, which translates to about $32 billion USD, with 1 trillion JPY already committed. The local construction frenzy is immediate.
And when the plant starts operations around 2027, even the initial core team will bring about 1,000 Rapidus employees and their families directly to Chitose.
Right, and we are seeing that investment appetite immediately reflected in the business community. We know that real estate development companies like Well Holdings from Fukuoka City moved into the Hokkaido market specifically because they saw the writing on the wall.
After the TSMC boom in Kumamoto Prefecture.
Exactly. They saw the blueprint for regional transformation.
And the data supports this, right? The land prices are just going crazy.
You're skyrocketing, completely transforming the local economic landscape. In fiscal year 2023, 4 of the top 10 nationwide residential land price rises in Japan were recorded in Chitose. 3 of the top 10 commercial plots were also there.
Oh.
This is a clear indicator that capital is flowing in, pushing out existing land uses, and causing concern among local property companies that general housing is rapidly becoming unaffordable for the average resident.
That seems like an inevitable headache for the municipal government. How is the local leadership, like the mayor of Chitose, managing this intensely fast, potentially disruptive growth?
They're responding with a focus on resource management and capacity building. The Chitose mayor is focused on continuously supplying residential land space to prevent housing shortages from choking off the incoming workforce.
And it's not just housing, it's businesses too.
Oh, yeah. The Chitose Chamber of Commerce and Industry has seen a near doubling in special members business operators based outside the city in just 1 year. This isn't just housing. It's a flood of supply chain businesses, supporting logistics, security, maintenance, and ancillary high-tech services relocating to the area.
So it's a full ecosystem being built.
It is. This is a regional transformation that other prefectures, such as Miyagi, are already trying to emulate, setting up dedicated offices to promote and attract the semiconductor ecosystem.
Okay, so the economic infrastructure is responding to the stimulus, but we have to address the single largest non-technical hurdle, the talent crisis. Japan can pour billions into concrete and steel, but they can't manufacture 40,000 engineers overnight.
That is precisely the Achilles heel. The industry consensus is that Japan faces an estimated shortage of 40,000 semiconductor professionals in the coming years. This is a gap caused by decades of underinvestment in the sector.
They just didn't train the next generation of specialists.
Exactly. Rapidus needs engineers who understand the intricate, finicky demands of extreme ultraviolet, or EUV, lithography, and gate-all-around transistor production.
40,000 is a terrifying number for a project that stakes national prestige on success. How can they possibly close that gap?
The strategy is multifaceted. It combines domestic training with aggressive international recruitment, and both of those present huge challenges. Domestically, Rapidus is partnering intensely with local institutions like Hokkaido University to build specialized, targeted technical curricula to fast-track new staff.
And the government is helping too with the LSTC.
Right. The Leading Edge Semiconductor Technology Center, LSTC, is also selecting dozens of students and researchers per year from Japan's top universities for highly specialized training programs.
But the reality is that they will need to rely heavily on attracting foreign, highly skilled talent to fill the gap. And culturally, historically, Japan is not known for having an easy or welcoming infrastructure for long-term foreign workers and their families.
That is the critical cultural and logistical friction point. It's one thing to attract a single engineer. It's another to persuade a family to relocate for 10 years.
Yeah.
The public support mechanisms for integrating foreign workers, schools, social services, language support have traditionally lagged.
So the broader economic impact has to aim to fundamentally improve the quality of life in these areas.
It has to.
I see. It's not just about the factory, it's about the town. If they can improve the quality of education and leisure activities, making Chitose comfortable and desirable for this sophisticated workforce and their families, they have a chance at talent retention.
And if they fail this quality of life test, the $32 billion factory might just become a training facility for other countries.
Exactly. It connects back to that human element, that old local saying, people who come to Hokkaido eventually leave. The goal of this investment is to reverse that decades-long talent drain, to convince the younger generation to stay in Hokkaido and join the Hokkaido Valley, rather than moving to Tokyo for opportunity.
This massive industrial policy is fundamentally a regional development strategy aimed at solving a demographic and generational problem.
If they succeed, the noise of the cranes becomes the sound of a generational curse being broken. Okay, let's now dive into the technical core of this national gamble. How does a company jump from a decade-old 40-nanometer capability straight to the 2-nanometer global forefront? This brings us to the structure and ambition of Rapidus itself.
Rapidus was established in August 2022, born out of this urgent national mandate. It's a national champion, funded by an unprecedented consortium of Japan's industrial giants.
Toyota, Sony, SoftBank, the big names.
All of them. Toyota, Sony, NTT, NEC, Kioxia, SoftBank, Denso, and Mitsubishi UFJ Bank. They're backed by immense government capital. An initial 70 billion yen, followed by an additional 260 billion yen allocated specifically for R&D and the pilot plant.
The mission is defined, mass production of 2-nanometer chips by 2027. But as we discussed, analysts are skeptical about skipping even one node. Skipping several nodes is considered almost technologically suicidal. What is the technical mechanism that allows them to even attempt this leapfrog strategy?
They are entirely betting on leveraging the most advanced international intellectual property and expertise. Their key technological lifeline is IBM. Rapidus is licensing IBM's breakthrough 2-nanometer technology, which is based on the advanced gate-all-around, or GAA, transistor architecture.
Without that partnership, the whole thing is a non-starter.
Completely non-viable.
Let's slow down on GAA. We need to understand why this specific transistor architecture is the key to scaling down to 2 nanometers. Why is the current industry standard, FinFET, no longer viable at this scale?
Right. So FinFET's fin field effect transistors have been the workhorse of the industry for the last decade. They essentially build the transistor channel into a tall, thin fin to allow the gate to control it from 3 sides.
Which was a revolution at the time.
A total revolution. Yeah. But at the 3-nanometer node, and certainly at 2-nanometer, the fins become too narrow and too closely packed. You start hitting fundamental physical limits where the gate simply loses effective electrostatic control over the channel. This leads to leakage current and poor power efficiency.
So leakage current is the enemy. Power starts bleeding away. That's where GAA steps in.
Exactly. GAA transistors, which are often referred to as nanosheet FETs, solve this by redesigning the channel entirely. Instead of a fin, the channel is fabricated as horizontal, stacked silicon sheets, nanosheets.
And the gate wraps around them.
The transistor gate completely surrounds or wraps around those channels on all 4 sides. This geometry provides superior total electrostatic control, it eliminates leakage, and it allows for much higher drive currents, all of which are crucial for achieving the density and efficiency required at 2 millimeter. IBM pioneered this technology.
Okay, so they have the technology license from IBM. Where do the R&D and the tooling commitment come from?
The R&D environment is international. Rapidus is a core member of IMF's Advanced Nanoelectronics program in Belgium. IMEC is effectively the global clearinghouse for next-generation chip research.
Right, they coordinate everyone.
They do. They coordinate universities, foundries, equipment suppliers. Their collaboration with Rapidus focuses intensely on the key enabling technology, extreme ultraviolet, or EUV, lithography.
And EUV is that complex, crucial piece of hardware manufactured exclusively by ASML of the Netherlands, required for etching anything below the 7-nanometer node. No EUV, no 2-nanometer.
Precisely. Rapidus has already secured a commitment for ASML EUV tools for the Hokkaido fab. This is a massive logistical feat because ASML's backlog is enormous. That initial 70 billion yen in government funding.
A lot of it went to ASML.
A significant portion was immediately dedicated to securing the purchase and delivery of 2 of these complex $500 million machines. The government essentially bought the keys to the future.
Having the license and the tool is one thing, but proving the process works is another. Rapidus recently announced a major milestone, successfully producing a 2-nanometer transistor prototype in collaboration with IBM scientists. That must have been a huge moment.
It was an incredible scientific feat. Rapidus CEO Koke called it unprecedented in Japan or globally in terms of speed. They went from formation to prototype in under 2 years. But the real significance is in technical detail, the specific hurdles they overcame to make GAA viable for mass production.
Let's dig into that aha moment. What was the specific technical hurdle at 2 nanometers that IBM and Rapidus solved?
The major challenge for any GAA architecture is achieving what scientists call multiple threshold voltages, or multi-VT. A modern chip needs transistors that operate quickly for high-performance tasks and transistors that sip power slowly for low-power tasks.
And multi-VT lets you create both types on the same chip.
Correct. But it's very hard to do with nanosheets. When you stack the nanosheets and try to achieve multi-VT, you run into immense challenges related to the metal gate boundaries and structural uniformity. The spaces between the transistors are incredibly tight, sometimes less than 40 nanometers wide.
So how did they solve it?
To solve this, IBM and Rapidus developed new techniques they call selective layer reduction, or SLR, approaches SLR1 and SLR2.
So SLR is the special sauce. It allows them to manipulate the extremely thin layers in that tight NP space, the space between the N-type and P-type semiconductor channels, to reliably achieve the desired voltage thresholds without introducing structural imperfections.
Yes. And according to Rukong Bao, a senior technical staff member at IBM Research, this new production process is simpler than previous, more complex approaches. Simplicity translates directly to better yield control when you move to mass production.
That's a huge deal.
This breakthrough reinforces the confidence that Rapidus can reliably manufacture 2-millimeter nanosheet technology at scale. Right now, this knowledge transfer is ongoing. Rapidus engineers are training intensely at IBM's Albany C&Z facility in New York,
getting hands-on experience with EUV processes alongside the key material and tool vendors who are also there.
That hands-on training is vital. It's about importing the culture of advanced manufacturing and the necessary technical know-how that was lost over the last 3 decades. Domestically, this effort is coordinated by the LSTC,
the Leading Edge Semiconductor Technology Center.
Right. The LSTC is the domestic brain trust. Established in late 2022, it serves as the coordinating umbrella, linking Japanese industry, government, and academia, including ACE, RIKEN, and the University of Tokyo to support Rapidus. Their research themes are explicitly tailored to bridge the gaps: advanced circuit design, GAA development, 3D packaging, and, critically, developing fast turnaround time, or TAT, manufacturing technology.
This entire synchronized ecosystem, international licensing, joint R&D, domestic research, engineer training, it's all designed to compress a decade of technological learning into the short window between now and 2027.
That's the plan.
This intense focus on speed brings us directly to their business model. Given the competitive landscape, where TSMC is already producing at 2 nanometers, how can Rapidus even justify its existence? They can't compete on sheer scale.
They have zero intention of competing on volume, and that is their critical market differentiation. Rapidus knows it cannot go head-to-head with TSMC and Samsung in high-volume commodity device manufacturing. Their strategy is speed over volume,
positioning themselves as a specialized leading-edge foundry.
Exactly, focusing on niche technologies that command a high price premium.
So what is the core selling point? If I'm a major chip buyer, why would I use Rapidus instead of an established giant?
The key is fast turnaround time, or TTO. Rapidus aims to produce and deliver custom chips tailored to highly specific end users' needs into us. Think military, unique AI accelerators, or specialized cloud infrastructure processors, 3 to 4 times faster than competitors.
So that speed advantage is their differentiating factor.
It is, in a global industry where time to market for a new customized design can take months. Their initial production volume is forecast to be modest, around 50,000 wafers per month, specifically because they are optimizing for speed and customization, not massive scale.
But isn't speed over volume sometimes just a euphemism for we don't have the process maturity to scale? How can Rapidus possibly guarantee such a faster path when they don't have the years of process control and supply chain maturity that TSMC has cultivated?
That is the multi-billion-dollar challenge, and it's the most significant risk to the business model. Rapidus's initial market base will primarily come from its consortium members, Toyota, Sony, SoftBank, and so on,
who are major consumers of advanced chips themselves,
and who have a national interest in the project's success. They provide the guaranteed first contracts. But scaling beyond that requires proving their yield rates and their ability to keep that TAT promise. The competitive challenge is immense, precisely because TSMC and Samsung have decades of experience in scaling.
Let's put that competition into sharp focus. TSMC already has commercial production of 3 nanometers and is reportedly achieving 2 nanometer equivalent yields exceeding 90%.
90%.
Rapidus, by contrast, has demonstrated a scientific prototype, but has zero experience in profitable mass manufacturing of advanced chips. The jump from prototype to 90% yield at scale is where most ambitious projects fail.
It truly is. The real-world volume know-how that rivals possess is almost impossible to replicate quickly. Rapidus is betting that the combination of IBM's design and their unique focus on quick custom turnarounds will attract a specific segment of the market that prioritizes customization speed over absolute lowest cost per unit.
And this high-stakes bet on Rapidus isn't Japan's only strategy. They're hedging their bets and securing their supply chain by simultaneously fostering partnerships for legacy and current nodes, right?
Well, absolutely. That is the smart, multi-pronged approach. They realize that while they chase the 2-nanometer future with Rapidus, they cannot neglect the urgent need for resilient supply of 10-nanometer to 40-nanometer chips needed today.
For industries like automotive.
Exactly. The best example is the partnership with TSMC in Kumamoto Prefecture. This joint venture, Japan Advanced Semiconductor Manufacturing, or JASM, involves Sony and Denso.
And the Kumamoto fabs are securing that immediate need.
Yes. The first fab there uses older but vital 12, 16, 20, and 28 millimeter process technology. This is critical for microcontrollers and sensors. Furthermore, they are already planning a second fab for 5 and 10 millimeter process technology, which is the sweet spot for current generation autonomous vehicle processors.
And Japan is providing huge subsidies for this effort, 476 billion yen, to ensure its colossal automotive manufacturing base is never again choked by chip shortages.
They're essentially paying their largest competitor, TSMC, to establish a highly resilient, geographically close supply chain on Japanese soil for the necessary nodes.
And we also see support for other foreign players establishing a domestic presence.
Precisely. The government has provided financial backing to Micron Technology for advanced DRAM production in Hiroshima and to the joint venture between Kioxia and Western Digital for 3D flash memory. The overarching strategy is clear. Increase the density of high-tech manufacturing within Japan's borders, foreign or domestic, to maximize supply chain security.
We've spent a lot of time discussing the parts Japan is importing, the know-how from IBM, the tools from ASML, the training from IS. But we need to talk about Japan's hidden foundation, the enduring strength that makes this entire effort even possible. Their indispensable dominance in semiconductor materials and equipment.
This is the critical piece that often gets overlooked, but it is Japan's long-standing, unacknowledged advantage. While they lost the chip manufacturing race after the 1990s, they never lost their global leadership in semiconductor materials and tools.
They hold key strategic bottlenecks in the global supply chain.
And every major foundry, including TSMC and Samsung, relies heavily on Japan.
This goes beyond just being a supplier. In certain areas, they hold a near monopoly.
A near monopoly that defines the industry. Let's look at the numbers. Japan holds over a 50% global market share in 14 of the most critical materials needed for chip making. For the foundational raw material silicon wafers, Sumino and Shinetsu Chemical together command a staggering 60% global market share.
You can't build a chip without Japanese materials.
You cannot. But where this gets really interesting is when you move up the value chain into the specific support equipment required for the most advanced nodes, particularly EUV lithography.
Right. The core EUV machine is from ASML in the Netherlands, but Japanese firms make the essential surrounding equipment.
They do. Take Tokyo Electron or Teitel. They have a near 100% share of the global market for inline coaters and developers for EUV. These massive specialized machines clean, coat, and prepare the wafer before and after it enters the ASML EUV scanner. If TEL stops working, the world's most advanced chip making stops working.
That near monopoly extends to the critical process of mask making too, doesn't it?
It does. For mask making for EUV lithography, Japanese firms JEOL and Nuflare hold a 91% global share. And the most sensitive component, photoresist, which is the light-sensitive chemical coating etched by the EUV light for Japanese companies.
Shinnetsu, Tokyo Oka Kogyo.
JSR, Fujifilm. They account for 75% of global high-end production. They hold a near monopoly on the photoresist necessary for EUV-compatible fabrication.
So if the U.S. controls the design, Taiwan controls the core manufacturing, and the Netherlands controls the scanner, Japan controls the fundamental materials, the specialized chemicals, and the support tooling that keeps the entire 2-nanometer process running.
That's the ecosystem. It explains how Japan maintained this dominance by focusing on the underlying chemistry and precision engineering that is hard to displace. It's the resilient strength of the Japanese ecosystem. They specialized in the things that require decades of materials, science refinement, and incredible manufacturing precision.
Which are difficult to transfer or copy quickly.
Very difficult.
Yeah.
And now they are leveraging this strength into the next frontier of chip performance, the back end of production, specifically advanced packaging and 3D stacking.
That's where performance gains are increasingly found now that process scaling is slowing down. Japan recognizes that assembly and packaging are now as strategically important as front-end wafer fabrication.
Absolutely. Rapidus plans to build integrated front-end and back-end production lines in Hokkaido. We are seeing major investments across the entire back-end supply chain. Kyocera, a manufacturer of advanced ceramics for packaging, is building its first new production facility in 2 decades.
Adventus is working with TSMC.
Right, a major Japanese chip testing equipment maker, forming technology alliances with TSMC for high-density back-end applications.
And the chemical suppliers are adapting too.
They are providing the specialized glue. Companies like Sumitomo Bakelite and Nissan Chemical are developing specialized materials, such as temporary bonding adhesives for complex 3D stacking. When you stack multiple dies logic, memory, I/O to create a powerful system and package, you need highly specialized materials to hold them together and then release them perfectly.
And Japanese chemistry controls that.
It does.
It seems like the decision by ASML, Applied Materials, and Lam Research, the key international equipment heavyweights, to establish bases in Hokkaido, alongside IM's plan to open a base, is a tacit acknowledgement of the irresistible strength of this underlying Japanese supplier ecosystem. They have to be there.
It creates a self-reinforcing gravity well. They have to be there because the people and the fundamental tools are there. Rapidus's entire strategic concept is to import the one missing piece, the advanced manufacturing know-how from IBM, and then plug that into Japan's existing, indispensable dominance in the material and equipment layer. This is how they plan to compress a decade of learning.
This high-stakes venture, however, is not without massive existential risks. Let's shift our focus to the necessary risk assessment. The sheer financial scale of this endeavor is the first alarm bell.
It is the largest single risk. We've repeatedly mentioned the total investment needed for full-scale mass production, approximately 5 trillion yen, or about $32 billion USD. While the government has pledged significant subsidies, we're talking about 1.7 trillion yen in commitments so far. Analysts universally agree.
It's not enough.
The current financing scale is still insufficient to launch and sustain full-scale mass production through to profitability. There is a massive funding gap that must be filled by private capital, either through additional equity investment or bank loans.
And relying so heavily on the state introduces the specific political risk that analysts refer to as the nationalization trap.
Exactly. The nationalization trap occurs when political and strategic imperatives override economic rationality. When the state provides the majority of the funding, the project's success criteria become political, like achieving 2 millimeters by 2027, rather than economic, like achieving profitable yield rates.
And this makes private capital hesitant to invest further.
It does, as they fear lack of capital discipline and future government interference, thus creating a self-fulfilling prophecy of state dependence. Japan has historical experience with state-backed technology projects that, despite vast spending, failed to achieve commercial viability.
Beyond the sheer money required, there are questions about the maturity and inflexibility of the business model itself, especially given how fast the industry is evolving.
The technological goalposts are moving rapidly. The 5 trillion yen mass production plan was finalized back in 2023. Since then, the industry emphasis has profoundly shifted from simple process scaling, the nanometer race, to performance enhancement through advanced packaging and 3D stacking.
And critics are worried Rapidus is too rigid.
Critics argue that Rapidus's current strategy seems too singularly focused on pushing the original 2-nanometer wafer fabrication plan forward without adequate flexibility to pivot toward hybrid bonding and 3D stacking as rapidly as TSMC is.
So they desperately need a plan B to adapt.
They absolutely do. If this were a purely private startup pursuing this enormous leap without gradually developing technology through prototype manufacturing, it would never secure financing. The tendency to push forward inflexibly is often cited as a weakness of large-scale Japanese industrial projects.
To be viable long-term, they need to be flexible.
They must demonstrate maximum flexibility to adapt its technology roadmap to market needs rather than solely fulfilling a national objective.
Let's consider the perspective of a foreign specialist who is headhunted for the Rapidus project. They might admit that the technical hurdle, the science, was solved by the IBM prototype. The real challenge is the engineering scale, the yield rates, and most critically, the 40,000 missing engineers.
Right. And they'd acknowledge that the strategy of focusing on speed is clever, but if they cannot hit those yield rates profitably, the speed advantage means nothing.
That combination of ambition, political pressure, and existential risk creates massive internal tension. For the veteran Japanese engineer consulting on the infrastructure, this project represents more than business. It's a national imperative.
It's a chance to restore the dignity lost in the 1980s. In a world where supply chains are increasingly weaponized and geopolitical tensions in the Taiwan Strait are rising, the Hokkaido factory is essentially Japan's high-tech insurance policy.
And that leads us to the ultimate question. What is the consequence if this monumental effort, this $32 billion gamble, fails?
Experts are clear. The timeline is absolutely unforgiving. If Rapidus cannot achieve full-scale 2-nanometer mass production with competitive yield rates within 2 years of its projected deadline, say, by 2029, Japan risks losing its relevance in advanced processes entirely.
And the failure would accelerate the technology drain.
Absolutely, meaning Japanese semiconductor and material companies, which we established are indispensable, might be forced to move their operations overseas to be closer to where the cutting-edge manufacturing, the profitable 2-nanometer production, is actually happening.
That would accelerate the talent drain and just weaken Japan's strategic position even further?
Exactly. The failure of Rapidus would effectively mean the abandonment of Japan's ambition in the advanced chip space for the foreseeable future. The focused concentration of capital, international technology, and institutional resolve is designed to create the necessary high-pressure conditions for success. But as we've detailed, the margin for error is razor thin. It is perhaps the single most significant industrial gamble Japan has made since the post-war recovery.
So this deep dive has really laid out Japan's multi-billion-dollar bet on Rapidus in snowy Hokkaido. It's driven by urgent national security concerns and really this fierce determination to reverse a decades-long decline.
The decline that began with the trade friction of the 1980s. The Rapidus initiative is unique in its strategy, supported by unprecedented international partnerships with IBM and IM, and strategically leveraging Japan's domestic indispensable strength in semiconductor materials and equipment.
And their market strategy, as you said, is a masterclass in focusing on a niche. Specialization and speed, that fast turnaround time, rather than trying to compete with giants like TSMC on sheer volume.
But while the project faces massive financial gaps, a critical talent shortage, and the inherent technical risks of leapfrogging multiple technological nodes, this focused concentration of capital, international technology, and institutional resolve creates the necessary high-pressure conditions for success.
The ultimate outcome, then, will not only determine the future of Japan's technology sector,
but also whether the serene dairy fields of Chitose, Hokkaido, successfully become the resilient, advanced heart of the new global digital supply chain.